Hi everyone, as it's just past the hour now, I'll get started with the webinar. So thank you everyone for joining. This will be the optics webinar on thin films and spectroscopic ellipsometry. My name's Rebecca, I work in the journal relations team for optics. If you're not aware with optics, optics is an MDPI journal. We're an open access publisher based in Basel, Switzerland, and we have over 493 peer-reviewed journals, and we're supported by over 295,000 experts all around the world who help us do what we do and publish what we publish. In terms of optics, we're an international peer-reviewed open access journal, and we publish our issues bi-monthly online. We're indexed in Scopus, ESCI in Web of Science, and EBSCO. We have a current impact factor of 1.6 and a site score of 2.6. And we are a very efficient publisher. We take around 56 days on average to publish manuscripts, and that includes getting a first decision back to the authors in around 22 days. This webinar is linked with a current online special issue within our journal called Optoelectronic Thin Films, and the deadline for manuscript submissions for this is the 28th of February. If you would like any more information on this, there is a link to visit the special issue on our website. For today's webinar, this is the programme that will follow. So very shortly, I'll pass over to our chair who will do some introductions for you all, and then we will have both talks and Q&A sessions from Professor Asknes, Professor Sasella, and Dr. Ermolov before the closing of the webinar at around 5 o'clock CET today. If you do have any questions for any of our speakers today, if you just put them in the Q&A box on the bottom bar of your screen, this will record them on the system and then we'll be able to ask them at the end of everyone's sessions. So for now, I'd just like to pass over to our chair, Dr. Politano, and she will take over the webinar from here.
Thank you, Rebecca. And welcome everybody to this webinar on thin films and spectroscopic ellipsometry. My name is Dr. Grazia Giuseppina Politano, and I am a postdoctoral fellow at the University of Calabria in Italy. I am an early editorial career board of the journals Optics, and I will be chairing today's webinar. First of all, I would like to sincerely thank our speakers, Professor David Aspnes, Professor Adele Sassella, and Dr. Georgi Ermolaiv for kindly accepting our invitation and for being here with us today. I would also like to warmly thank MDPI and the journal Optics for their support of this initiative and for making this webinar possible. As an early career scientist, I truly appreciate the opportunity to coordinate this event, and their trust and support have been essential to its realization. I would also like to sincerely thank Rebecca Paget and Belle Sang for hosting today's webinar and for their excellent support throughout the event. And finally, I would like to thank all the participants for joining us today. We hope you will enjoy the webinar and that it will be both informative and inspiring. And this event is conceived within the framework of open science with the aim of promoting the free exchange of knowledge, fostering discussion across disciplines, and supporting the scientific community through open and accessible dissemination. In line with this spirit, each presentation will be followed by a dedicated question and answer section, and participants are warmly encouraged to actively engage by asking questions and sharing comments. Before starting, I would like to briefly introduce the scientific context of this event and the idea behind the program. Thin films play a central role in many modern technologies, including electronics, optoelectronics, and photonic devices. From transistors and sensors to optical coatings and integrated photonic components, thin films are everywhere. In this context, spectroscopic ellipsometry stands as one of the most powerful and characterization techniques for thin films research. by analyzing changes in the polarization state of light upon reflection or transmission. Ellipsometry provides access not only to film thickness and optical constants, but also to a wide range of material properties associated with variation in optical response, including composition, crystallinity, surface and interface roughness, doping concentration, and structural inhomogeneities. Since the 1960s, ellipsometry evolved to achieve the sensitivity required for measuring nanometer scale layers in microelectronics. And today, its application extends far beyond microelectronics to encompass fundamental research in physical science, as well in industrial fields such as semiconductors, data storage, flat panel displays, communication, biosensor, and optical coatings. And the widespread adoption is driven both by the increasing reliance on thin films across many technologies and by the remarkable flexibility of ellipsometry, which can be applied to an exceptional broad range of material systems, including the electrics, semiconductors, metal, superconductors, organic materials, biological coatings, and complex composites. At the same time, the reliability of ellipsometry analysis and of spectroscopic techniques in general critically depends on the quality of the experimental data. For this reason, a core theme of this webinar is noise removal in spectra through linear and nonlinear methods, which represents powerful tools for improving data interpretation. So the first invited talk will be delivered by Professor Dr. David Aspnes, and I would like to sincerely thank him for accepting our invitation. And as I said, his contribution have had a profound impact on spectroscopic ellipsometry, and they continue to inspire young researchers in the field. In parallel, this webinar highlights advanced thin films materials and their characterization for optoelectronic application. And the scientific program will continue with two invited contributions addressing ellipsometry studies of functional thin films and emerging materials for optoelectronics. So the second speaker will be Professor Adele Sassella, and I thank her for accepting this invitation. I'm very honored. And her contribution will focus on the ellipsometry investigation of porous polymer thin films. The third invited speaker will be Dr. Georgi Ermolaev, whose contribution addresses wafer-scale quasi-two-dimensional gold and its potential for optoelectronic applications. And I thank him for accepting this invitation. So I would like to express, first of all, my sincere and heartfelt thanks to all the speakers for generously accepting this invitation and for bringing their inspiring high-impact research to this webinar. And before moving to the scientific program and introducing each speaker in detail, I would like to briefly mention that this webinar is connected to the special issue Optoelectronic Functional Thin Films, currently open in the journal Optics. The special issue focusing on recent advances in functional thin films for optoelectronic application, spanning areas such as luminescence, energy generation, and conversion, imaging metamaterials, and metastructure. More broadly, it aims to provide a platform for interdisciplinary research addressing the relationships between materials, structure, and optoelectronic performance. In this sense, the webinar and the special issue share the same scientific spirit, fostering high-quality discussion, cross-disciplinary exchange, and deeper understanding of thin films material and their optical and optoelectronic properties. Further information on the special issue is available on the webinar website, and interested participants are warmly invited to explore it. So now it is my pleasure to briefly introduce Professor David Aspenes before giving him the floor. Professor David Asmnes will present a talk entitled Removing Noise in Spectra by Linear and Nonlinear Methods. Professor Aspnes received his PhD in 1965 from the University of Illinois, Urbana-Champaign. Following a year as a postdoctoral research associate at UIUC and another at Brown University, he joined Bell Laboratories, Moore Hill as a member of the technical staff. In 1984, he became head of the Interface Physics Department of the Bell Corps, the part of the Bell Laboratories that went with the operating companies in the AT&T divestiture. He joined NC State University as a professor of physics in 1992 and was named Distinguished University Professor of Physics in 1999. Thank you, Professor Aspnes, for being an inspiration to young researchers working in the field, and I now give you the floor.
Okay, I think you can hear me. Let me go to share, and I am to put on screens. Somewhere is PowerPoint. Everything's working. You should be able to see a slide here, and you should be able to hear me. I wanted to give credit to my co-workers in this project. This project actually started probably when I took my first spectrum in the mid-70s. And there's always, of course, noise present, and you want to get rid of it, and you want to figure out the best methods to do it. And this has been an ongoing project, and it picked up steam when I had some time over in Korea some 10 years ago, and picked up a grad student who's now at the Vietnam Academy of Science and Technology in Hanoi. So let me just go starting and getting involved with the topic. The real challenge is to remove noise, but the challenge is to preserve the information. And any idiot can remove noise. You just run your signal through a low-pass filter, but that destroys the information. And so we want to be able to do both. Keep the information and remove the noise. And in order to do this, well, of course, this has been a problem that's been around for a long time. Kaiser and Reed complained about it in 1977, Barrett in 1995. And the question is, how do we do this? I gave a preliminary version of this talk at a summer school about 8 years back, and the fellow who organized it had some advice to everybody. He said, take better data. That's good advice if you can do it. We're going to look at some XPS data from gold clusters with sulfur on them scattered over an oxidized silicon surface. There aren't too many of them. And if we look at the L23 soft X-ray threshold of sulfur, this is what we get. We get a J equals 1/2 over at about 164 eV binding energy, and a J equals to 3/2 at 163. There's two features in here, and there's a bunch of noise. And I apologize that this isn't an ellipsometric spectrum, but on the other hand, this is a particularly good spectrum to talk about noise removal because the noise is noticeable, but it's not so bad that it's beyond repair. And so this is what we're going to be working with for at least most of this talk here. Okay, so how do you get rid of noise? Well, the old days you did direct space convolution. You took your favorite point, you added the value of the two adjacent points, you divided by 3, and there was your filtered point, okay? And then you went through the entire spectrum doing this. That's fine, it smooths it, gets rid of some of the high frequency stuff, but we can do better. Move on to 1964, the whole field really started then with Savitsky and Golay. Let's take those 5 points off on the far right. We're a little bit more sophisticated. We multiply the midpoint of your favorite point by 17, adjacent points by 12, next points over by -3, and we divide by 35 at the bottom here, and we get the result of a filtered spectrum here. Well, we look at that, and the red curve is the filtered result, and it's kind of a disaster. We realize that it's done a very good job of protecting the noise. Well, let's see if we can do any better. Move on to 1983. This filter I like because you can roll one out yourself. It's the Pascal triangle. If you're not familiar with it, take a look and see how the pattern develops. we're doing 5-point smoothing down at the bottom, the 1, 4, 6, 4, 1 weighting, we divide by 16. We now look at our spectrum again, and hey, this is a little bit better. At least we've made some improvement on that. But the question is, what else can we do? Well, we can do this, which is the boxcar filter 5 points. Instead of doing 3 points, let's do 5 points. Add 5 points together, divide by 5, and look at the result. And hey, now we're making real progress. Okay, so but we're missing something. And this is what I was trying to build up to. Somehow, even though we're using 5 points and weightings, we get very different results for the 3 approaches that I put on the screen. Well, what's going on? And the answer is what's going on is happening in Fourier or reciprocal space. Let's look at the data again and take a good look at it. Where are my features? There's 2 of them, and they're point-to-point correlations, okay? Let's look at the noise. It's point-to-point fluctuations. And if you don't get anything out of this talk, keep this in mind, that the information is going to be in the long wavelength or low end of the Fourier coefficients. The noise is going to be in the high end, the short wavelength stuff. So we Fourier transform this thing, and this is just repeating what I said verbally, so we don't really need to look at it. The main point is down at the bottom, that information and noise then are separated in reciprocal space or Fourier space. And here's Fourier transform, which I won't go through into any detail. R sub n are the complex coefficients on the top line up here. Theta are f of j over here. And here's your Fourier transform function, e to the minus n theta j. And we get through with this, we take the Fourier transform of our spectrum, and we find out that, yes, this is exactly what happened. Number of the coefficient order is down at the bottom. There's 111 points. We get 56 coefficients out of this thing. And we look at that. What we're plotting here is actually the absolute magnitude of the Fourier coefficients on a log scale. And what we see is that 50 of our coefficients are wasted on noise, okay? And only 6 coefficients do we have to work with. And if you look at that 6, you see that it's decreasing more or less linearly with coefficient index. That means that if you go back to the regular representation, that means you're dealing with an exponential decay. This tells us we're dealing with a first order decay transition. Okay, fine, this is what you'd expect. And the beat pattern in there says that we've got 2 structures that we're dealing with. But anyway, let's get back to filtering again. The dumb way of doing this is we just do this. We say, well, every coefficient above 6 is noise. Let's throw them all out, okay? And let's just reconstruct now in direct space the coefficient, taking these 6 coefficients down here and turning them back into direct space. And there you have it, okay? It's a much better filtered result than anything we did earlier. So the main thing that's come across here now is that in reciprocal space, you got separation of information and noise. And once you have that, now you can start talking about how best to resolve the noise issues. Okay, so anyway, what I did, I introduced inadvertently kind of a transfer function down here, which is also called the winner function. I took those coefficients, the first 6 I multiplied by 1, okay? And the last 50 I multiplied by 0. And that technically is called a transfer function. Now, the trouble with this crude transfer function is that is a phenomenon that's characteristic of Fourier transforms in general. It's called ringing, okay? And ringing is a problem because anytime you try to cut off a Fourier series directly, you're going to get that. And so are there better ways to do this? Yes, there are. One way to do it is a so-called Gauss-Hermite function, and that takes the coefficients, and I don't have a dot to really point to here. So let's take a look at the left side of these coefficients, again, the lower 6. And you see basically what I did is I multiplied them by 1, and then I multiply it by a function that decreases as a Gaussian as I go to higher and higher n. And so by the time I get to n equals 15, essentially everything is left over. This gives me a slightly better version than the brick wall filter that I talked about a little bit earlier. but as you can see, there's not a lot of difference, and you almost have to be a specialist in order to appreciate it. So basically, we have linear filtering under control, okay? We go into reciprocal space, we throw away the noise, and we keep the information, and we Fourier back transform in that, and then we are basically finished with our filter. Now, the filter that I used was a filter introduced by Hoffman and co-workers back in 2002. As of yesterday, it had 18 citations. 10 of those were ours, okay? And so it basically disappeared without a trace. Now, I'm talking filtering, but I'm also talking how to present your results so that people pick them up. What happened? Why isn't this used everywhere? Well, the answer is Huffman et al. Published it in a somewhat obscure journal, Computational Physics Communications. And what was worse is they expressed their transfer function as a product of, or as a sum of Hermite polynomials. Now, anybody who's a physicist has a very bad feeling about Hermite polynomials. They are solutions associated with the harmonic oscillator. It's quantum mechanics, and nobody likes quantum mechanics. And so don't ever put your results out in this form here. What they should have done, which is indicated on the bottom down here, if you take that expression under alternate form and go all the way to the right, this is e to the minus x squared, okay? And everybody knows that. That's just a plain old Gaussian. And look at the power series expansion multiplying that. And those of you who are still with me here will recognize that as the first 5 terms of the power series expansion of e to the plus x squared. And so what we have cleverly done is we've knocked out the first 5 terms of a Taylor series expansion of this function at around n equals 0. In other words, we've developed a flat top equal to 1, and then the thing falls off a cliff basically catastrophically at the end. And you cannot beat a filter that does that. That's the sort of thing that is ultimate in our filters, and then we can take that and run with it. Okay, can we get some insight yet as to what happened with our other filters who didn't work out so well? Yes, we can. Let's go and Fourier transform the boxcar function, or let's Fourier transform these functions themselves. We are taking advantage essentially of the convolution theorem that a convolution in direct space, which is what we've been doing, is equal to the product of the Fourier coefficients in reciprocal space. So here are your transfer functions. Your data is a black curve, okay? And again, this is now on a linear scale rather than the log scale. Coefficient index down at the bottom. And here is our first 6 coefficients. That thin line that you can hardly see tells you where your information basically cuts off. And now we look at the Fourier transforms of the transfer functions that we had. Savitsky, Golay, the first one that did an excellent job of preserving noise. As you can see its value is nearly equal to 1 up until about 30. It drops to 50%. We are passing most of the noise, okay? So if you Fourier transform that transfer function, you can see right away why things went bad. If we look at the next one, the binomial, a little bit better. It hits 50 at about 20, so we're leaking less noise. If we go to the boxcar, the red one over here, that cuts off at about 10. And anybody want to guess what the Gauss-Hermite looks like? No comments? All right. This is what it looks like, the black one over here. And so as you can see, it holds 1 up until 6, and then it drops off fast. And that's why we argue that you cannot really beat that as a Fourier transform, as a filtering function. Okay, so again, we're Fourier transforming the transfer functions. We're looking at them in reciprocal space. We're comparing them against the Fourier transform of the data, and we're matching things together to get the best possible filters. Well, we're talking window functions. Okay, if you go onto the internet and you look up window functions, you'll find 31 of them, right? This is from Wikipedia, and they're all named. I mean, these are just the named ones. And if you look hard at that, you'll not find Gauss-Hermite on that list. Well, how are we going to sort this stuff out? Here's one of the new things that's come up within the last several years. There's now an equation that we have that can quantitatively assess whether your transfer function's any good or not. Okay. In other words, this over on the left side here is the square of your total errors in the entire spectrum between your spectrum and your filtered spectrum. Okay. N is the number of points. And there's two terms in there that matter. One is labeled degradation, one is labeled noise. And let's take a good look at them. B is your transfer function coefficient. If you want to avoid degradation, that has to equal to 1. Okay. If that's the case, then this first term vanishes. Well, it shouldn't be. Am I losing it here? Yeah, okay, let's bring it back. Well, now I may be in deep trouble. Let's see where we go. Yeah, okay. Yeah. Okay. So in the first case over here, if B is equal to 1, then you don't degrade your signal. But if B is equal to 1, check your second term out, you pass all the noise. And so you're not doing any filtering. On the other hand, if B is 0, you want to kill all the noise. It turns out you killed the signal as well. And so that doesn't work either. And so what we learned from this expression are several things. One is that you cannot construct a perfect filter. Unlike quantum mechanics, B cannot be both 0 and 1 at the same time. You got to make a decision. You're going to save the information or you're going to degrade, you're going to save the noise, one or the other. Second thing is that the function itself has the data in there. And that means that there's no one size fits all linear filter. Okay. You got to have this, you got to make a decision. And the third thing is not really a part of it here, but I'll get to that in a minute. And that is the X-size tail, which we haven't talked about yet. When you use any linear filter, you're cutting off a part of your information, and so you tend to get ringing out of that. On the other hand, you can determine what your optimum cutoff is going to be, and that is when those two terms are equal. As you increase the n, the degradation term is essentially going down exponentially. That's typical of the Fourier coefficients of the spectra that we look at. And the noise, of course, is constant. It's white noise. And so when the two terms become equal, that's when that's what you set for the extent of your filter. Gauss-Hermite can do that. Brick wall cannot. Boxcar cannot. And so that's another reason why Gauss-Hermite is simply a better filter. If you got to make a decision, you go on the side of noise because the first term is decreasing exponentially with increasing n, and the last term is essentially constant invariant. And so that teaches you then from this expression here what you should be doing about linear filtering, and that essentially summarizes linear filtering in a nutshell. Okay, let's move on to nonlinear filters. I want to say a few things about them. I won't get into a lot of details on them, but we will at least come up with something. Linear filtering did pretty well, but it's still a compromise. Okay, you got this degradation versus leakage that you got to deal with. If you cut things off too fast, you get Gibbs oscillations or ringing. And then it didn't mention anything about apodization. Okay, apodization is an interesting error because if you cut off let's see, how do I want to do this? Let me go one step. Yeah, if you cut off when you start cutting into the white noise region in here, you're also cutting into the information, all right? You might not realize that there's a tail of information going down into the white noise region, but the mathematics does know that, okay? And that's where your errors are coming in. And can we beat this? Yes, we can do it with nonlinear filtering. So I'm now switching the topic from linear filtering, where we're just attenuating coefficients, to nonlinear filtering, where we're replacing coefficients. And this diagram shows you the idea behind it. Here's our data once again up at the top. You got 6 points that you can work with. You got 50 points worth of noise. I don't show all 50 here. Here's the Gauss-Hermite in blue dropping off as attenuation. And then this red curve I want to talk about. That's the one we're interested in next. Okay. What that red curve is a result of what's called the corrected maximum entropy theory. And what that theory does is it extracts the trend in the lowest 6 coefficients down here, and it extrapolates it forward into the white noise region. Okay. And once I have that, I can throw away all these coefficients for n greater than 6 and replace them. That's the nonlinear operation is replacement. I can't reverse that, okay? It's a replacement here, and now I got the best possible filter that I can get. I've got taken care of this tail that's coherent, that sits under the white noise region. This is an analytic extrapolation. And as a result, it has no noise at all. Okay, so now you got the best of both worlds, and this is a new area in filtering that really hasn't been pushed before. Forward extrapolation, and this is something that's going to be really the wave of the future in all this. Linear works by attenuation, nonlinear works by replacement, and essentially what it tells you is if you took a straight edge and a pencil and you laid the straight edge on this plot up here parallel to the lowest 6 points and they just drew a straight line, you would get a better filter than anything you can do with linear processing. Okay, so in any case, that's another message that you might want to take away from this discussion. Linear is attenuation, nonlinear is replacement, and we now have the mathematical tools where we can take these trends and extrapolate them into the white noise region. Okay, so what can we do with all this? If I go ahead and do this, okay, here's my usual plot of the data with the filtered material putting on top of it. And of course, that doesn't mean a lot other than it's nice. But if you put it now against the Gauss-Hermite, the blue, you see that there's a little bit of difference on there. Again, both filters are passable as far as general purpose filtering is concerned. But you see the red one is a little bit higher at the peak, okay? Why is that? Well, that's your coherent tail coming in. Gauss-Hermite didn't include that, okay? And the peak, of course, depends on coherency. And so you got rid of this tail that extends into the white noise region, and that cut down your peak. Bring it back, and your peak goes up again, okay? And so once again, if you want to do the ultimate filtering, you got to go nonlinear. There's no other way to do it. Let's see what I got for time here. Yeah, I think what I'm going to do is this started out really as a, yeah, I guess I'll just put this up here. Keeps the low order coefficients intact, projects and model dependent trends into the white noise region. And why entropy comes into this thing is that it adds the least amount of new information. And then therefore, as the people tend to say it, that maximizes entropy. And now I'm going to skip over some slides because I don't have time really to go through it in detail. We don't care so much about the history of entropy or the conversation that Shannon had with von Neumann. But I am going to go over what the CME does and how we can do it. Okay. So anyway, what this thing does, if you just look at what the lines are up here, given n+1 values of a function, first m+1 Fourier coefficients, r sub n down here, generates an expansion p of theta. In other words, the coefficients are sitting in reciprocal space, your expansion's back in spectral space, okay? And the curve that is generated, the first m+1 coefficients agree exactly with what you started out with, okay? And that's the extracting the trend, and then you extrapolate it forward. What does this look like? Again, this is going to be recorded, and presumably you'll have this available. This is the recipe to getting this famous P of theta up here. It is the inverse of the absolute square of a finite sum, okay? And finite, I'm going to emphasize that. This is not an infinite Fourier series. This is a finite series. It's got these coefficients a sub n. How do you get them? You solve a matrix equation down here. The coefficients of your r's, your complex Fourier coefficients, multiplying this vector of coefficients a is equal over here. You can solve this thing, and when you get done with it, you can get a result that looks like this. P of theta ends up looking like a product of absolute squares of simple poles, okay? And this is kind of neat because if you take one of these things and expand it, writing, here's my expression on the top again, you let a1 over a0 equal e to the minus broadening parameter, and you end up with an expression on the third line down here. And now if you multiply the denominator by e to the gamma, you end up with an expression that's cosh gamma minus cos theta. If you do a small term expansion of this function, then you get the Lorentzian, okay? And this thing is rather interesting because you also get this from the Fourier, discrete Fourier analysis of a continuous, of a discrete spectrum. Down at the bottom here, you're looking at a continuum. Here, you're looking at a discrete spectrum. You never see this, but this is the way, again, the future is going to look on these things. Okay. Here we got some ellipsometric data and to show the kind of games we can play with this stuff, all right? Molybdenum diselenide, 31 degrees Kelvin, thin film, fine energy range from about 1.5 to 2 eV. Two structures in there, two main features. Each of them is split. There's a neutral exciton and the charged exciton. We would like to be able to pull those features out, okay? And that is a filtering problem. Normally what we do is we differentiate twice with respect to time. If we do this, I'll come back to this in a minute. If you do the differentiation twice with respect to energy over here, you get the black curve, and obviously you're not going to see much in that. On the other hand, if you go the maximum entropy route, here are your coefficients down at the bottom, n over here. Here's log of the absolute value of the coefficients. This time you get about 40 coefficients to work with. Okay, so you got something you can get your teeth into at least. Here's your white noise level starting at about 40. Here's your trend extrapolated. You now replace all these coefficients in black beyond 40 with those in red. And now you go ahead and you do your differentiation on that, and this is what you get. No noise, okay? Which is what you'd expect because you've replaced all those bad coefficients with analytic coefficients, and they have no noise on them. So that's what you can do. And this is ellipsometric data, so you can deal with that. Okay. If you go play the same game with the gold data that I showed you here, then you get, in this particular case, you get 5 poles. 2 of those that matter are down at the bottom down here. One is near 164 EV and the other 163. This on the left-hand side is your J1 half. On the right-hand side is your J3 halves. And you got 3 other poles to deal with. They're mainly cosmetic. They are the ones that are using to get the line shape correct, essentially. But once again, you can pull out then the energies of those poles. They're not entirely accurate, but they're close enough to get some interesting results out. Let's see. What else can I say on that? Yeah. Without going into details on this, you can also play games with this analytic feature. You can replace the theta variable that you're looking at with theta minus I alpha. That shows up in your cosh function down here. And the curve, or the equation second from the bottom, notice what's happened when I go through this. What I have done is I have provided an opportunity for reducing the broadening parameter, okay? And what can we do with that? Well, we can do things like this. We're going to try to find a biexciton in this. Again, ellipsometric data, tungsten disulfide, 50 degrees Kelvin, energy range 1.5 to 3 EV. And I now apply my corrected maximum entropy approach to this, and I get a spectrum down at the bottom. Okay, it's just a spectrum all over again. Now I start cranking down the broadening parameter. All right, at alpha equals 0, it just reproduces the original spectrum. Okay, alpha equals 0.05. I've started to cut into the broadening parameter, and as you can see in the blue curve, we're starting to sharpen things up. Alpha equals to 0.1. Fantastic. We now have the main exciton isolated. All right. Next one, the A0 is coming up next to it as well. Still haven't quite got to the B excitons yet, but if we go to 1.135, the green curve at the top, now you got all those features showing up. In the B case, you got the double over here, doublet's been split. Then the A case, out comes the biexciton down at the bottom. So this is another thing you can do with a nonlinear processing that you cannot do with linear, okay? What else can I say? Well, this is just a repeat of the same thing where we're just moving this up a little bit more carefully here. I think that that probably, I'm running short of time on this, so I'll probably stop at that point. And let me skip over several other view graphs and come to a conclusion. Oh yeah, this I won't say anything about because we have done that also with with X-ray diffraction. That was an X-ray diffraction measurement that we did with some other groups. So this is actually quite general. So anyway, this kind of summarizes where we stand at the moment. Okay, linear filtering, we got that very much under control. Gauss-Vermeet is presently the best filter to use. That will change, I'm sure, now that we have a quantitative assessment availability here. This is going to improve, but at the moment, Gauss-Vermeet is it. In any case, now you have optimal filtering for linear processing. CME, okay. That's the nonlinear group, next three lines down here. CME, as you can see, has a whole lot of possibilities. It also has a dark side, and that is it only works for Lorentzian lines. Throw in any dispersion curve, and it doesn't work. We have fixed that, although I don't have any of this results in here. That's been in the last few weeks. And so now that can be allowed, these games can be played with any spectrum. So we get rid of apodization errors and we get rid of the noise errors. Okay. And the approaches that we've talked about here are moving beyond ellipsometry. They're getting into X-ray diffraction. The area that's really been excited about this is X-ray photoemission, because they're particularly interested in getting chemical binding information out. And there you need to be able to pull out small shifts and get these accurately determined. So this is kind of where we stand. And if you want more information on that, these are the publications we have up till now. And I am open to questions. Thank you very much for your attention. That was a lot of information in a short time. But hopefully, if you want more information, I do respond to emails. Okay, and so if you need more information on that, let me know. The paper that covers the quantitative assessment of linear filtering goes in. It's going into the Journal of Applied Physics. It's been essentially accepted. We had to do some changes on it. I'm going to resubmit the corrected version tomorrow. Should be out in the next several weeks or thereabouts. Anyway, open for questions.
So thank you, Professor Asmenes, for your inspiring talk. And are there any questions from the participants? If you have some questions?
I can see two have been asked in the chat, so I will answer them. I'm not sure, are you able to see them if you click the Q&A box? They're quite long, so it might be better if you read them
Yes,
directly.
Let's see. Chat
We
is
can
one.
see them, yes.
Yes, great. If you open the Q&A box, there's two questions there for you.
Okay, one of them is, well, let's see, all I can say. No, if you can read them, that might be easier because I don't see anything. Oh, wait a minute, hold on. It says more down here. To Q&A.
Just next to where you share your screen, there's
Yeah.
a Q&A
Okay.
box.
Yeah. Thank you for the presentation. Could this noise filtering approach be applied to infrared ellipsometry experimentally? Yes, you can. This is utterly general. These examples that I gave were basically examples that describe the particular approaches particularly well. But no, it works. That doesn't matter where you do it. Okay. And let's see what else. The bottom one down here. Did I lose it? That seems to have gone off the deep end. Wait a minute, let's try once again. You would like to answer this question. One is just thanks for an interesting talk. It's not a question, that's a comment. Thank you for the comment.
The other is from Dr. Thomas Wagner. Yes.
Oh, okay. Can you repeat that for me then? I cannot read it.
Yes. So okay. So it said, "Dear David, quite interesting. You talked about it in general. Could you please comment if there is anything in particular to apply to ellipsometry? Are you consider this to apply just on results of optical constants or already on psi, delta, NCS data? Thanks." So it's like by Dr. Thomas Wagner.
That's a good question. We have not tried it on psi and delta, but we could. There's no reason why you can't. Basically what you're handed is a spectrum, and what's the definition of a spectrum is just a set of intensities as a function of some variable, energy or wavelength. We describe everything in terms of theta because it's Fourier analysis and it's just more convenient to work in from minus pi to pi. But you give me something that is a set of points from one end to the other that has a information content that is a broad spectrum underneath, and it has noise, which is point-to-point fluctuations. Yeah, we can get rid of the noise and concentrate on the information. That's really the only requirement, that the information have a broader characteristic than the points.
Yes. And actually, there is another question. So I don't know if you reply, like, thank you for your great presentation, Professor Asmnes. My question is, could this noise filtering approach also be applied to infrared ellipsometry experimental data, in particular in the low frequency range between 400 and 500 centimeters -1? We sometimes observe a residual noise that prevents a good fit, even when the signal-to-noise ratio is relatively good.
Yeah,
Yes,
it's
yes.
again, all you need really are features, the information content that's broader than the point-to-point fluctuations. The separation is done in reciprocal space, and the essential ingredient here is that the low index coefficients have the information and the high index have the noise. And so I don't care what you're handing me, where it came from, whether it came from ellipsometry, whether it came from infrared spectroscopy, Raman scattering, or X-ray photoemission diffraction, anything you want. As long as it fits that description, you can apply these approaches. Yes. Have him send me a example, and I can go offline. I won't do it here, but if he wants to send me email me an example, I will go through it with him or her.
And another question by Alexander Treffer. Would it be a good idea to apply to raw data as it would change it and maybe filter out some characteristics?
Yeah, anytime you want to get the noise out of there, again, it doesn't matter what the data are, psi, delta, anything at all. As long as you got that separation in reciprocal space, low index got the information, high index has the noise. That's all that's required. And every noise signal I've ever seen falls into that category, at least the random stuff, the white noise. Yeah, so that should work under most anything you guys can throw at me. I should be able to deal with it. At least that's the challenge I throw out there. How about that?
And there is another question by John Patrick Harris that the purpose behind describing this with XPS is it's because it's easier to pull out the bioexciton energy in XPS versus ellipsometry. It is easier to get the energy information with XPS information.
No, the only reason I used XPS is that the noise, first of all, it has two structures in it. So you got features you can relate to. And the noise is basically cosmetic. It's large enough to be annoying, but it's not large enough so you can't get at the information. So XPS is used as an example, okay? Biexciton doesn't come out of XPS. It comes out of ellipsometry. Big difference. XPS is hundreds of EV typically. Broadenings are EV, 10 EV, and so it's an entirely different area of the frequency domain to work in. You can't use XPS to get the biexciton.
Yes. So I don't see any other questions from the chat. I don't know.
I do have a question, if possible.
Yes.
Well, just a note. Thank you very much for the talk. As an experimentalist, we are always dealing with noise, so thank you very much. I understood that selecting the proper filter, for example, linear or non-linear functions, transfer functions, permits to control different characteristics. Am I wrong? I mean, selecting a particular transfer function, you can preserve better intensities or attenuation, while selecting other transfer function, you can mostly control resolution so that you could see the biexcitrons showing up. Or is there any indication in this direction, which would be very, very practical, I mean?
The answer is the linear filter cannot pull those excitons out. Okay, that was a result of the particular mathematical form of the corrected maximum entropy result. Okay, and with that result, we can throw the mathematics in there that decrease the broadening parameter, and that's how I was able to pull this out. Okay,
I see.
so the poles were in there, and by decreasing the broadening parameter, then you pick them out one right after the other. And so that's strictly a nonlinear process. You cannot do that with linear filtering.
I see. I see. Thank you. Thank you.
Yeah, the nonlinear allows capabilities that linear does not. And on the other hand, I'll mention this again, that the nonlinear approach that I talked about here only works with Lorentzian lines. Okay, if you throw any dispersion character in there, like the real part of the dielectric function, it doesn't know how to deal with it. And the reason is if you remember that expression, it's 1 over the absolute square of a polynomial. Okay, absolute square means it's positive. Okay, it means it's positive definite. It's worse than that. If the noise shows excursions that go negative, you got to put an offset in. And so we are working around that because there are other ways to do it. In a general sense, that the linear filters take your noisy spectrum and they work back to the information. The nonlinear filters start with a model line shape and they work out towards the noise. Okay, so there are two filters that are actually very complementary in their approaches. You figure out what the result should be, and then you can start putting in the Fourier coefficients to go back more and more to reality. That's a paper we're working on now, and it'll be a while before we get it done probably, but that's what's going to happen, is that we'll find that the linear goes from the noisy to the noise free, whereas the nonlinear goes from the noise free to the noisy. Okay. And so it depends on where you get off the trolley that matters.
Thank you. Thank you.
Crazy stuff. This is the
So,
sort of thing you can do when you're retired, okay? You can't do this when you're out trying to raise money from NSF. They will not fund work like this.
I understand. I understand.
Okay. Yeah, filtering has already been done. Everything that's to be said about it has been said, and suddenly you realize that it hasn't been said. And so this is the other thing that's going on here. So,
Thank you.
so are there any other questions from Professor Asmus? And another thing is that just like to read all the questions that Dr. Maula Khan Ziermal thanks Professor Asmus for its great presentation. And
thank you.
yeah.
And again, I
And
answer emails. So if you have further questions, send me an email on that. So, unfortunately, I have to leave, but in any case, it's been a pleasure. Okay.
So, Professor Asmus, thanks for your enthusiasm. It's an honor for us, and thank you very much. And as I said, you're like an inspiration for a lot of researchers working in this field. So, thank you. And
Okay.
so, if there are no questions, I think that I can introduce the next speakers if there are not any other questions. So, okay. So now it is my pleasure to briefly introduce Professor Adele Sassel. Professor Sassella will present a talk entitled Ellipsometry Study of Porous Polymer Thin Films, Refractive Index Tunability. Professor Adele Sassella is a full professor of experimental condensed matter physics at the University of Milano Bicocca since 2016. At the beginning of her career, starting in the 90s, her research focused on impurities and defects in single crystal silicon, as well as on silicon-based dielectric thin films. Since 1997, she has worked on organic molecular materials, which have become her main area of research. Her activity was at first devoted to the establishment of a laboratory for the deposition of thin films and heterostructure of organic molecular materials under ultra-high vacuum using organic molecular beam epitaxy. Subsequently, the characterization and study of the deposited samples became the central focus of her research. Her work has addressed thin films and heterostructure belonging to several families of organic materials, and including acridines and oleogenesis, enable comparative studies within molecular families. A key aspect of her recent research is the selection of crystalline solid substrate that promote epitaxial growth of the material of interest. This approach allows precise control over the morphological and structural properties of the grown films. And through numerous national and international collaboration, the structural and light emission properties of the grown system are also investigated to reach a more comprehensive understanding of their physical properties. So, Professor Adele Sassella, now I give you the floor. Thank you. It's an honor for us. So thank you for accepting our invitation.
Thank you, Grazia. Thank you very much. I hope you can see my starting slide. Do you?
Yes, yes.
Fine, fine. Thank you very much. I'd like to thank, of course, Grazia Politano for inviting me. We never met, but we know each other a little bit.
Yeah.
And of course, I thank the organizers and the Journal Optics for this opportunity. My seminar will be much more focused, less general than the previous one by Professor Aspers. It's focused on the study, a recent piece of work we did on porous polymer thin films, where we tried to characterize the refractive index, checking for the tunability of the index itself. So, here we are. As a broad background, the frame where this research can be considered is the need for low refractive index materials, which is something, of course, related to any applications or devices where light guiding and or confinement is necessary. So light emitting devices, detectors, optical fibers, or devices for transmission of optical signals. There are several approaches. At the beginning, the first one was, I don't know if you can see my pointer. Do you? No, probably not.
Yes, we see the arrow.
The arrow. So the first approach was using low index material as coatings. For example, in fibers, actually, this is the starting point, or preparing nanostructured materials layers for by etching the materials themselves. But here we are addressing a different approach, which is indeed already proposed by several people in the last years. So preparing materials, in particular polymeric materials, thin films, which are porous. So comprising some pores, some void inside, can give rise to low index with respect to the refractive index of the bulk materials. In this in the materials which can be treated to get porous polymeric films, two materials are the most promising one and have been already demonstrated to give rise to porous structures. They are syntactic polystyrene and polydimethylphenylene oxide, PPO. As you may imagine from my slide, this PPO is the material we were dealing with, and I will then discuss about porous PPO thin films and about their refractive index. This work is not exactly on the materials I'm working with commonly, usually with my group, but the interest arose while collaborating within a national project with a group of chemists dealing with polymers, and in that project I was in charge of the optical characterization, so I could address this new family of materials with in a technique we are using in Milan. So our approach, but as for the synthesis, it was from a group in Salerno involved in the project. So our approach was obtaining porous PPO films by crystallization, by a process which led to partial crystallization of the amorphous bulk material by using a cost-effective and green process. These are two reasons why the whole work is interesting, and it is particularly relevant also from the point of view of the materials and of their synthesis. The processes influences both crystallinity and porosity, and this was known, but the process was not yet adapted to grow thin films. So actually the films are prepared in advance, and then the process of crystallization, solvent-assisted crystallization, can be applied to get porous thin films. The process can be controlled, and this is something we could demonstrate, to tune such a crystallinity, which was known in the bulk, to tune then porosity, and therefore also the refractive index. So the aim of this specific work, my work, was determining the refractive index by spectroscopic ellipsometry. Here are the samples we studied. We actually measured much more samples, but this is a homogeneous series in the sense that we have the starting amorphous film, the nanocrystalline, which is the amorphous one treated to get as much as possible crystalline film, and then something intermediate, low porosity and high porosity, I call them. And immediately you can see that the samples, the films are highly inhomogeneous. You can see here different colors, here as well. The films scatter light, in particular this, which has a high porosity, is gray, it's whitish, so suggesting that light is scattering. We had an amorphous reference, it's an amorphous PPO, just prepared following a standard process, so it's our reference, and you can see even by eye in the picture that it is much more homogeneous. Our samples were all deposited by a spin coating on crystalline silicon, single crystal silicon, and the same silicon, exactly the same, was also used as a reference measured by spectroscopic ellipsometry, and then the parameter fixed to be able to use always the same conditions as data for data regression. We have various degree of porosity and crystallinity, and the problems I already mentioned. This is the instrument we use, the Boolean-based ellipsometer with its software, and these are the experimental conditions to get typical experimental data, which are psi and delta, as we all know, but also we can collect the depolarization signal. This is rather bad in the sense that depolarization expresses how much light gets depolarized upon reflection. We are working in reflection mode, so that it's a measure of how homogeneous, how good is the sample, how good is the measurement given some critical characteristics of the sample. And this is something we always measured and tried to model. These are just the experimental conditions, and now the first problem was how to model such films, which even by eye look rather complex samples. First, we had to characterize them, and some problems arise actually from characterization. From the infrared absorption spectra, one can, and this is a common technique for polymer physics, one can estimate by looking at specific peaks, absorption peak, one can estimate the crystalline fraction in the film. For example, here, this is the typical amorphous peak, which is shifting when crystallization goes on, and some new peak appears here, again, is a signature of the crystalline phase. Analyzing the spectra for 3 of our samples, of course, the partially crystalline one, we could get the crystalline fraction, and we end up understanding that the nanocrystalline sample is not as crystalline as we thought. Well, at least myself, being not exactly deep into the subject of polymer physics. So the first basic idea, trying an effective medium model, was not perfectly perfect to apply, in the sense that we had not the extreme amorphous and crystalline and one of the two porous. We had some mixed phases. Then we went to check the transmittance in the UV visible, and we saw the amorphous and nanocrystalline films transparent, transmitting light, and then this is the edge of the substrate. Of course, these were deposited on silica. While the two porous samples were clearly affected by scattering, a little bit the first one, and more the high porosity film. So we ended up with the new information. Not only we have scattering from pores, but we can estimate more or less how big these pores are, about a few hundred of nanometers in size. But this was also confirmed from scanning electron microscopy, because we could see, this is just one example, we saw a really rough surface and full of holes, so we could estimate also the mean pore size. But we could also see some regions, some linear or fibril regions, or the white, the more brighter ones, which are the crystalline phase, and which are known, they are part of the crystalline phase, which is known to possess a porosity over a different scale. This is a known result for several polymers. When they crystallize, this is just a sketch from the literature, inside the crystalline in itself, there are some pores, so the structure is somehow affected by porosity over a scale which is orders of magnitude smaller than the other. So we have two phases, amorphous and crystalline, with two types of porosity. So we started from the most crystalline one, the nanocrystalline sample, which is not completely crystalline, but it does not have the macro porosity, not detectable at least. So the nanocrystalline so-called sample was modeled just by considering the silicon we already characterized in advance as a substrate, as a clean substrate, plus a layer which is transparent as we measured, as we observed by UV visible transmittance, so that its extinction coefficient is 0. We just took a Cauchy-like dispersion and tried to fit the data. So the black curves are the experimental data, the red one is the fitting curve, the best fit. Of course, a simple Cauchy cannot model in any way the depolarization. There's no way. So we added the so-called thickness non-uniformity. Is a parameter in the software which accounts for the possibility that the thickness is non-uniform over the region probed by the ellipsometer. And actually, some depolarization could rise due to that inhomogeneity. So exactly what we were looking for, and then we refined one more step, adding the surface roughness, so a layer with PPO, amorphous PPO plus void. And we got at the end something rather satisfactory where the error is about 6, 7. Consider that the error can be as low as 1 or 2 in the definition of the software we are using. So this is in some sense satisfactory, and we went to the other to the extreme, so to the amorphous film. Here the problem was limited in the sense that taking silicon, then a Cauchy layer plus non-uniformity, we could get some good results, even if one has always think about having something better with lower noise and lower errors. But we had to face with another problem. If we take the same sample and we measure over a millimeter size spot, a macroscopic spot, or over a microscopic spot, over 100 micron or so, for example, in the real sample, these two are the two microspot corresponding to the measurement which could give just model in this same wave two different curves in terms of refractive index. So we found out that the inhomogeneity in thickness imposes actually us to use microscopic spots. So we discarded these measurements, and among the two different spots, or actually even more than two, we selected the one which, upon regression of the data using the same model, could give us something which was closer to the reference amorphous, which we took, performing the same measurements and the same analysis, we took as a reference. So the amorphous PPO film produced, synthesized with the standard process. So at the end, among the different spectra, we took this green one collected on a specific region, small region, as our refractive index for our amorphous film. Then we had to face with the two intermediate porosity films. So not amorphous, not crystalline, or better, partly amorphous with macroscopic pores of about 200, 300 nanometers in diameters, and the crystalline phase with the nanometer size pore inside the crystalline unit cell. So these are the two films with low and high porosity, but rather complex samples. Here we could get a rather good fit using, again, the same substrate plus Cauchy-like layer and non-uniformity, which has to be taken into account for modeling depolarization, plus some surface layer, mimicking roughness in some sense. So we got a rather good result in terms of errors and of fitting. And then we addressed the high porosity one, but nothing good happened unless we take care also of scattering by means of an effective extinction coefficient, which actually just account for scattering. I can show you, well, this is the best fit, which has a rather high error, but nonetheless good if we look at how scattering is the sample and how inhomogeneous. I can show very briefly you the first step. This is just a Cauchy-like layer on the silicon, and this was the first attempt, but nothing was working. Just adding the effective absorption, we realized this is the good way, because fitting is much better here. But in any case, we need some tricks to account for depolarization, but we already know which is the trick. The trick is non-uniformity in thickness, which permits some fit also of the depolarization signal. And at the end, adding roughness, we got what we believe it's a reasonably good result. So back to our results. I'm close to the end of my seminar. Here is the whole series in terms of refractive index. So we have the amorphous, and again the dashed line is the reference pure PPO and completely amorphous film of the literature and of the standard synthesis, nanocrystalline, low porosity, and high porosity. So our colleagues, chemists in Salerno, succeeded in tuning structure, I mean porosity in particular, and therefore tuning the refractive index. To make a comparison, here I just listed the values at 600 nanometers. We have from amorphous to nanocrystalline to low porosity and high porosity 57, 1.52, 44, 39. When the best, the reference, literature reference for low index polymers is polytetrafluoroethylene, which has 1.38 in the index of refraction at 600 nanometers. These are the parameters coming from the regression of the data, and I can come to the conclusion. So we succeeded, in my opinion, to treat such complex film, demonstrating how actually the solvent-assisted crystallization of amorphous PPO film can give rise to a tunable refractive index, but just by tuning the process, the synthesis from the amorphous PPO to this nanoporous, macroporous. I spoke about two kinds of porosity, which is their characteristics. This is the results in terms of refractive index, and we are happy about the coherence within the series. We are happy about the agreement between the amorphous, which took us some time and some work to understand properly and to work with them, and not very relevant actually result. The thickness coming from ellipsometry was in perfect agreement with data collected by a mechanical profilometer over I can show you in each of our samples, we left one corner without film on purpose. We covered the corner to be able to perform a measurement, a mechanical measurement here of the thickness, which was a check for our thickness measured by ellipsometry as one of the parameters coming from regression. So the agreement was very good, which is a very strong support to the whole work. So in conclusion, again, we believe we successfully used the spectroscopic ellipsometry for rather complex films. We believe we succeeded in setting the crystallization process for tuning and controlling crystallinity and at the end refractive index. We did have some problem of reproducibility of the process and sample inhomogeneity still to be addressed and solved. So I thank you very much, but I thank my whole group, the OMBE group, the group I'm leading at University of Milano Bicocca, Alessandro Minotto and Luisa Raimondo, who are the senior scientists and PhD and postdoc collaborators. Ilaria took care of most of the experimental work on spectroscopic ellipsometry. We are part of the spectroscopic network of our university, so I'm indebted to them when I discuss with all of them. And I thank very, very much Paola Rizzo, who's the colleague in Salerno. She's expert of PPO, of polymer thin films and porous thin films. And she and her group were the ones who opened our interest into this particular kind of materials which we didn't know before. I of course thank the funding from the ministry, and this is the project we were involved in. And again, I thank you all very much.
So thank you, Professor Sassella, for your outstanding talk. Are there any questions? I think that there are like some questions. Okay, let's see if okay. So there is a question by Dr. Thomas Wagner that is saying, "Dear Adele, nice to see you again. Very clear and systematic experiments. It is quite typical that layers with large porosity causing scattering can be described with virtual absorption. But we still need to keep in mind that Fresnel equations are no more exactly valid. That's why we still not be able to fit the data perfectly. Thickness, non-uniformity, and bandwidth allow to fit the polarization, for example, meeting Fresnel. But with scattering, there is still the polarization which cannot be modeled."
Well, I thank very much Thomas Wagner. I know him since years and years. I'm very happy he agrees about the way we treated our samples and our data. I agree with you, Fresnel coefficients and Fresnel equations no more work so that we can try to manage in some way, but I'm convinced we did some valuable work. And I showed you just a small series of samples, but we had some confirmation also from different samples prepared even months later just to check everything, because they have actually some problems of reproducibility. So thank you very much, Thomas.
And then there is another question. I actually cannot read because I think that it's written in Cyrillic, the name, but there is like, "Dear Professor, thank you for the great experimental presentation. Could you elaborate, please, on the model of effective extinction coefficient? What was it exactly in the fitting software? Waves, I suppose. Was it part of the Cauchy equation or other layer in the whole model?"
So the extinction coefficient is a part of the Cauchy model. You can add it. And it is effective in the sense that you know it's not a real absorption. You know it's not a proper extinction coefficient. But since you lose light intensity due to scattering, the effect at the end is the same. So it's a fictitious extinction coefficient which accounts for some loss of intensity. Is similar as an absorption, but it's due to scattering. But you can find it. Of course, I wrote somewhere the software is the WVASE of the Vullam company.
Yes. So yes, actually, I don't see other, I think, questions. I don't think that yes, there are other questions. Then okay, there is
May I
like
ask?
the reply of yes.
May I ask
Yes,
also
yes,
the
yes, for
questions?
sure.
Yeah, and
Yes, for
you
sure.
mentioned this high porosity you reached. What is the maximum porosity you reached in your samples? with this
Yeah,
1 point?
they measured by the BET technique, which is a technique where a gas is put is forced to enter the material. And if I'm not wrong, I can check, but if I'm not wrong, this was the maximum was 35%. Sorry, I'm checking the numbers.
Yes, good.
Yes, 33 for the high. No, sorry. From BET measurements, we had 45 square meter per gram for the high porosity film, while for the low porosity, we had 130 square meter per gram. But for the nanocrystalline sample, we had undetectable surface area because the nanocrystalline samples just have that nanoporosity within the unit cell of the crystal so that any gases can enter there.
I see. Yes, thank you. Very interesting talk. Thank you.
And actually, there is like the comment of Dr. Thomas Wagner from Hulam that says that it is in the Hurbach absorption part of Cauchy.mat. I think that is replying to the question
Yes,
where is
the
yes, on
K,
the software,
yes,
yes.
yes, of course.
Yes, so yes. So thank you, very. I don't think that there are other questions. If there are other questions, I don't know. I don't think. Yes. Sorry. Yes. There is like the reply that they thank you for your answer because Ivan Kotsko about MIPT. So he thanks you. And then there is a question by John Patrick Harris where he said that did you also try a genosk.mat file to model your film to see if the MCE could be improved?
No, actually, we didn't. We tried with some effective medium just to check, and it did not work. And not well, it did work on some samples, but not on the high porosity ones. But did not. I did not try with the oscillators because, as far as a simpler model works. I want I don't like to use more complex modeling, but it's a good idea. We will try because we try to go on with our colleagues in Salerno. Thank you very much.
And Dr. Maula Khan Ziarmal thanks you a lot for your presentation.
Thank you. Thank you very much.
Yes. So I don't see any other question. So if there are not any other questions, I really want to thank you for your outstanding contribution. It was like a very inspiring yes, I don't see actually other. Actually, John Patrick Harris, thank you. Thank you, and for your presentation and other. Yes, I don't see any other questions, and so thank you again for your outstanding outstanding talk. And if there are not other questions, and only just one question, like from me, if you see that if there are other next steps in this research on these films.
Yes, absolutely. With my colleague in Salerno, Paola Rizzo, we are planning not only new samples because she's always working on the process, but the idea is to try to follow the process while it happens. So to synthesize the samples in Milan, not in Salerno, and checking step by step on each single sample what's happening. This is our idea.
Okay, so thank you very much. And
Thank you again for the invitation.
Thank you for accepting this invitation. We are very honored. And so thank you. And so we can move to the next speaker. So it is my pleasure to briefly introduce Dr. Hermolive before giving him the floor. Dr. Hermolive talk is about wafer scale quasi two-dimensional gold for optoelectronic application. Georgi Ermolive received a PhD in broadband optical properties of molybdenum disulfuride for photonic application in 2022 from the Moscow Institute of Physics and Technology. After receiving a PhD, Georgi Ermolive became a research studies manager in Dubai, United Arab Emirates, which is in a HADEP tech company specializing in next generation optoelectronic devices. In 2023, Georgi Ermolive also joined the University of Rome, Tor Vergata, as a visiting researcher. His research interest encompasses various areas such as ellipsometry, 2D and quantum materials, integrated nanophotonics, biosensor, plasmonic scanning, near-field optical microscopy, and smart contact lenses. Georgi Ermolive has an impressive publication record with over 50 published papers and more than 1,500 citations during the last 5 years. So, Dr. Georgi Ermolive, thank you for accepting this invitation. And the floor is yours.
Yes, thank you very much for inviting me and for this marvelous event. So, as Grazia mentioned, I will speak about wafer scale quasi two-dimensional gold for electronics applications. So basically, my part will be mostly about thin film. So I will focus on applications because I'm from the industrial part of the science, but still there is a lot of science will be and spectroscopic ellipsometry as well. But before I begin, I just wanted to make a few words about the company. We are located in Dubai, in the United Arab Emirates, near the famous Jumeirah Palm. So if you are visit Dubai, we are very open. You can see our laboratories and all the equipment we have. So now we have a large R&D teams of more than 50 researchers, with half of them holding a PhD and very broad expertise from microwave electronics to biosensing and photonics. And we have also a very broad research field, starting from smart contact lenses, materials for photonics, two-dimensional materials for optoelectronics, biosensors, synthesis of various nanoparticles, even including some fancy van der Waals nanoparticles, and also we're doing a lot of machine learning for photonics and material science. We have a great team on artificial intelligence. And in today's talk, I'll focus on two-dimensional materials for optoelectronics. And to begin with, I would like to start my talk with a novel lecture of Andrei Game, Random Walk to Graphene. In this novel lecture, Andrei Game provides the concept of metallic electronics, which actually lead him to discover graphene. And he recognized that if an external electric field is applied to a metal, the number of charge carriers near its surface changes, so that one may expect that its surface properties change too. This is how modern semiconductor electronics works. And he suggests why not use a metal instead of silicon. And in the same lecture, he answers that with standard materials like gold, it's very difficult because maximum field for dielectric is around 1 Gauss per nanometers, which translates in maximum charge carrier concentration change of around 10 to the power 14 centimeter minus 2. It gives only around 1% conductivity change for 1 nanometer thick gold. So basically, we need to go really atomically thin to get these effects. And hence the question arises whether it's possible to create quasi two-dimensional gold, so this atomically thin gold with only few nanometer thickness. And the problem is that it's very challenging to synthesize atomically thin gold, because usually gold is produced using the physical vapor deposition techniques such as thermal evaporation or electron beam evaporation techniques. And usually the gold formation follows the so-called island growth or Volmer-Weber mechanism, and before producing the continuous films, first gold atoms form an island. But ideally, we would like to have a layer-by-layer growth to produce atomically thin gold. And you can see here shown is what we wanted to have as an ideal mechanism, because in that way we can really go to atomically thin gold of few nanometers. Otherwise, for now, the current techniques only produce continuous gold films of only around 20 nanometers. And the solution how to reach atomically thin golds is the use of an additional adhesion layer. So the idea, for example, you can grow, you can grow your gold, for example, on another metal, on a copper, because of the large metal-metal connections. It's really produce a really nice morphology and thickness, even within a few nanometers. And also you can use otherwise, for example, two-dimensional materials. There's also really nicely grown gold on molybdenum disulfide. Otherwise, you can use some organics seed layers, which also can produce atomically thin gold with a smooth morphology. And what this techniques uses is they use the thermodynamic energies of the substrate of absorption energy to the gold, because actually in our system we have two energy. The surface energy of the gold, which actually combines, if it's very high, it will comparing to absorption energy, then it will produce the ion formation. And we have also atom to atom cohesion energy. And for example, if we consider gold grown on the silicon dioxide on a certain substrate, then because its absorption energy is very much below gold surface energy, then it will really produce ion formation, because it's much easier for gold to form ion instead of film on top of the silicon dioxide. But for example, if we consider molybdenum disulfide gold on molybdenum disulfide, it already has the absorption energy close to the surface energy, and because of that we have the percolated films, as you see on the scanning electron microscopy. But if we, for example, grow gold on the copper, then you can see we will produce a continuous film, because the gold copper adhesion energy is very close to the gold cohesion energy. But there are several problems with this technique. That okay, it produces additional adhesion layer, provides ultra thin and ultra smooth gold, and it was shown in numerous publications. But the problem is you cannot transfer your gold from the copper, so you don't need gold on a copper, you need it on some device. So the problem is after the growth, so unclear how to detach gold from the seed layer. And actually, the second problem is that additional adhesion layer usually deteriorates the optoelectronic properties of ultra-thin gold films. And hence, we have the ideal substrate is a copper, but it's unclear how to detach gold from copper. But we can think it from the two-dimensional technology, and from two-dimensional technology, probably most of you know that graphene also grown on the copper, and for graphene, a similar problem is already solved for chemically vapor deposition grown graphene on a copper. So the idea is the following: we adjust the technology of the graphene on the left side of the presentation. So you can see there is a typical graphene transfer technology, and we can apply the same technique for the gold. So the idea is the following: in a graphene transfer technology, we have the copper, then the chemically grown copper, graphene on the copper, then we cover the structure with the protective polymer layer. Then using the electrochemistry or chemical dissolution, we can remove copper from the graphene, and then clean our samples and transfer it on the desired substrate. And actually, we can apply the same technique for the gold. So we can cover our silicon substrate with the copper, deposit the copper, then we can deposit gold film on top of the copper, then cover it with a protective layer, then using electrochemistry illuminate copper from the substrate and then dissolve copper. In the end, you will receive the gold with the polymer, transfer it and remove the polymer, and you have your gold on the desired substrate, for example, in your device. So you can see it's very much similar to what is in graphene technologies produced. And in fact, this technology produces a really nice morphology of the gold. So you can see even down to 2 nanometer thickness, 3 nanometer, 5 nanometer, 8 nanometer, the morphology is very continuous. The roughness is below 0.4 nanometer for all these thicknesses. So you can see RMS is 0.41, 0.38. So it's very smooth thin films. And actually, we also make the transmission electron microscopy measurements and observe that the crystal structure of these synthesized gold films is the same as for the bulk gold. So its properties should be similar to the etalon properties. And indeed, we make the measure ellipsometry of these gold films and also reflectance, transmittance measurements. And you can see from this data, we obtain a really nice optical properties, which nicely described by Drude-Lorentz oscillators. And epsilon real part of the dielectric permittivity is below 0, which is a sign of a metallic optical response. And actually, for example, you can see here that plasma frequency is very close to the bulk plasma frequency. However, damping factor of the Drude oscillator is increasing because when we decrease the thickness, the scattering from the surface of the film start playing a major role because it's starting to be comparable to the free mean path of the electron. And also you can see we verified our optical constants with transmittance measurements, and you can see the experimental data are very nicely reproduced with the calculated transmittance based on optical constant from ellipsometry. And on top of that, we investigated how plasmons propagates inside these films. So basically it's gold, so it can support the plasmon. So using the near field optical microscopy, we excite the plasmons, and you can see here how they propagate. And surprisingly, we observed that with using the local model, which we get used in ellipsometry, cannot reproduce the high propagation lengths of our plasmons, and you can see that plasmons propagates larger than it's predicted from ellipsometry. And the reason for that, because actually in this atomically thin films, we have the non-local response, so that charge is distributed over the screening layer, and you can see because of that the current decreases, and because of the decrease of the current decreases the ohmic losses, and the plasmons propagates further. And because of that also, and other effects, that it's very close to the bulk properties, we observe that our films demonstrate a really nice conductivity. So it's really small resistance. So we can see its sheet resistance is comparable to indium tin oxide, and even outperforms the famous graphene, CVD graphene sheet resistance, and have one of the best trade-off between the transmittance and sheet resistance. Because, for example, if we wanted to use a transparent electrodes, we need a high transparency, but also a very small sheet resistance. And this is exactly the case for our ultra-thin gold films. And for example, we can use it in optoelectronics applications. As an example of these optoelectronics applications with our two-dimensional goals, we created flexible organic light-emitting diodes, and we use replace the indium tin oxide anode with the our ultra-thin gold films as an anode, because it not only gives you greater mechanical flexibility because of replacing brittle indium tin oxide with a flexible ultra-thin gold, but it turns out that the gold has a better Venn diagram, so you can see it provides much smaller energy difference to P dot PSS, which facilitates transfer of the charges, and because of that, you can see a very robust shining of the OLEDs and much better current density, much higher luminescence of using ultra-thin gold films as a replacement of indium tin oxide. And you can see it's a very scalable technology, so we can make an array of these OLEDs on a large scale and very flexible, and ignite each OLED by applying the voltages. And also it could use, for example, in the thermal camouflage, for example, we covered it with satellite, and you can see that indeed, if we cover it with a satellite, it's becoming more invisible to thermal radiation, and actually because it's emits less thermal energy, which is very nice for thermal management in space applications. For example, we have a close connections to Dubai space missions, and the reason for that is because we have really nice reflectance of the gold. So the gold reflects a lot, and because of that, as we know from the Kirchhoff's law, it will produce a smaller absorption and hence smaller emissivity, and then according to Stefan Boltzmann law, it will produce less emission of the radiation, thermal radiation, and will result in effective thermal camouflage. And it could be also used, we tried it on the hands or whatever, so it really works nicely. And in other applications of this two-dimensional gold is the wearable electronics. So basically, for example, you can probably heard that now it's very popular to place some electrodes on your hand. Actually, this is how electrocardiograms is measured, but they use doctors usually use gel, but argentum chlorine. But instead of the gels, we can use the gold tattoo covered with your hands, and then the record electrocardiogram, and also we tried electromyograms to measure your muscles activity, and you can see that indeed your signal becomes more clear. So in the signal noise ratio increases for gold tattoos comparing to the standard gel electrodes, and also similar properties observed for electromyograms. And you can see, so it's really could be nicely used in medical applications as a wearable electronics and so on. And we did it in collaboration with our colleagues in the University of Massachusetts, USA. And to conclude, I wanted to, I think I persuaded you that graphene transfer technology is really nicely works for two-dimensional gold. So basically, two-dimensional technology is not only applicable to two-dimensional materials, it's also can be applicable to other materials like gold. And also we demonstrate that using this technology, we provided two-dimensional gold with excellent optoelectronic properties. Is one of the best properties, and as a result, we use them as a flexible transparent electrodes and use in different applications in space technologies, in OLEDs, and also in medicine applications. This is our article. If you wanted to see more details, so also we are now preparing another article. And thank you for your attention. Feel free to ask any questions. Thank you.
So thank you for your outstanding presentation. Actually, there is a question from Dr. Thomas Wagner. He asks you, Dear Georgie, very interesting presentation. As you compared gold epsilon 1, epsilon 2 for different layer thicknesses, had this been pseudo-optical constants or determined layer optical constants as they change with thickness, which would indicate change in density in case of layer optical constants?
Yes, it's a good question. It's not pseudo dielectric function, it's a real dielectric function from the optical
Yes,
model.
the dielectric
And
function.
yeah, the dielectric function. And as you see, I probably didn't mention it. As you can see, for down to 3 nanometer epsilon, the real part of the epsilon is the same, which actually shows that its density of electrons is the same. But the optical losses increases because the surface starts playing the role in scattering mechanism of the electrons. But for example, if we're reducing the thickness, you see now it becoming less electrons because of that the real part of the dielectric function increases. But down to 3 nanometers, you can see the dielectric function of the real part is very close to the gold. And that's why actually the reason why plasma frequency is the same. But the optical losses increases because of the surface effects of the gold. Yes, that's good question. Thank you.
And there is another question by Abdullah Al-Shamarri that it thanks you for your presentation. And then the question is, what about the electrical performance stability of two-dimensional gold electrode considering the heating effects in optoelectronic devices?
Yes, it's a good question. Actually, we didn't observe any, let's say, heating problems, for example, in OLEDs and other devices, but we didn't apply too much currents. So in these devices, because, for example, in OLEDs, if you apply too much currents, it will burn your OLEDs. But it's a good question. Probably in more in other applications, we believe that it will be robust because gold electrodes will not have any problems with it. Should not, but we didn't check it yet. Yes, we have plans to do that. Thank you.
And I think that there are not other questions. Okay, if
No,
I don't know if
grazie.
yes.
Grazie, it's me.
Yes, sorry, I didn't read the chat, yes.
Sorry. May I ask?
Yes, sure.
I'm curious to see some experimental data in the way you model it, just the ellipsometry. An example, if you have, because it's something I never studied directly.
We tried the usual, Drew the Lorentz model. So it's Lorentz is we use Lorentz because you can see in the short wavelength regimes there is interband transitions in the gold.
Yeah.
But with for long wavelength regime, we need to account the contribution from the free electrons, and this free electrons is nicely reproduced with the Drude response. Probably I should have included the formula.
So you had to mix the two, I guess.
Yes. You need to include both to account for this effects. That's right. Yes.
I understand. Thank you.
Welcome.
And actually, there is another question by Dr. Thomas Wagner. How did you avoid the parameter correlation between thickness and optical constants?
It's a good question. For now, we didn't. We know the thickness because when we deposit the gold, we can adjust our quartz calibrator to have exactly thickness we wanted to. So we don't fit it in the optical model. We already know what is the thickness from the during the deposition system. In deposition system, we're already measuring it using the quartz mass system, and also we verified this thickness with atomically forced microscopy. But you're right that if we wanted to try to fit the thickness, it will be overfitted and it will not get reliable results. So that's why we need to know the thickness in advance before modeling. That's correct. We actually observed below 10 nanometers, you cannot, but above 10, it's already some, you can avoid correlation, but below 10 nanometers, at least for our films, there is a strong correlation, yes, between optical properties and thickness.
So I don't know if there are other questions. I think no. So like my questions is like, what are the next steps in this research in the study of ellipsometry of 2D gold? Do you think that it can be improved?
Yes, actually, we wanted to include non-local model in ellipsometry. So we wanted to excite plasmons, but not using the near-field microscopy, but using the ellipsometry, for example, using the prism, and observe this non-local phenomena, because it's really nice to have this non-local response, because it reduces your ohmic losses. And for example, you can create much better, for example, surface plasmon resonances, resonator biosensors, and all these nice applications and physics, because it's really interesting physics behind these non-local properties. Usually researchers works in a local model, but for atomically thin materials like any graphene, whatever, molybdenum disulfide, you name it, you need to apply non-local model, because it's all these ultra thin materials are essentially non-local. But usually it's hard to get this non-local response, and usually it's a negative effect, but for our ultra-thin golds it's a positive effect, and it's really observable. Yes, thank you for the perspectives questions. Lot of work to do, right?
So thank you really for your. Actually, Dr. Thomas Wagner said that from the previous question that it was the only way to solve it. The thing that the thickness was fixed. Yes. Because to deal with the correlation, actually.
Right.
And so actually, are there any other questions? For the speakers, I think no. So okay, before closing the webinar, I would like to thank all the speakers for the amazing contribution, and I would also like to warmly thank MDPI and the Journal Optics for their support of this initiative. I would like to sincerely thank all the participants, including the many well-known experts from both academia and industry who joined us today. It is a real honor, and it has truly been an honor for us to have such a distinguished audience, and we are very grateful for your interest, your time, and your engagement. And I would also like to highlight the mission of Open Science that strongly guides this initiative. MDPI and the Journal Optics actively supports open access as a way to promote the free circulation of scientific knowledge, foster transparency, and encourage collaboration across disciplines and communities. And events like this webinar reflect that mission, bringing together researchers, industry representatives in an open and accessible forum to share ideas, discuss challenges, and inspire future developments. I really thank Rebecca Paget and Belle Sang for hosting today's webinar and for their excellent support throughout the organization of the event. And today's talks have provided useful insights into spectroscopic analysis, thin films materials, and optoelectronics applications, and that they will stimulate further discussion, new ideas, and possible collaboration. And finally, I would like to invite you to visit and explore the related special issue. And actually, I will the special issue, which is that you can find on the webinar webpage, is optoelectronics functional thin films, where many of these topics are further developed and where you are very welcome to contribute. And I would like to thank you all once again for being with us today, and I really thanks all the participants that have shared their comments and we really appreciate your enthusiasm. And before I conclude, I would like to give the floor to Rebecca Paget, should she wish to say a few words on behalf of MDPI.
Yes, thank you everyone for joining us today. I think it's been a very educational, very collaborative webinar, which is always very nice to see. So thank you to all of our speakers for taking the time to be with us today, everyone for watching, and everyone who asked a question as well. It was really nice to hear people's opinions. I know we've had one more question about wanting to get in contact with some of the speakers. If you email optics@mdpi.com, we can get you in touch with anyone that you'd like to be in touch with from this webinar as well. So yes, thank you everyone for joining, and I hope that we can see each other again soon.
Yes, thank you very much.
Thank you very
Great.
much. Thank you very much. Thank
Thank
you
you.
very
Ciao.
much.
Again.